Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back everyone to ITDR2103. In this session we will discuss about lecture 7 and 8 of this course, since they are discussing the same topic, which is recursive definition and recursive applications. In this session we will discuss first about lecture 7, where we will define what do we mean by recursive definition, and we will find how we can find the recurrence relation from a sequence, and then we will see how we can do the vice versa, where we have the recurrence relation and then we can create the sequence. Then we will move to lecture 8 topic, which is the recursive application, where we will have a look on how GCD of two integers is defined recursively, and then we will see the other applications of recursive definition. Let's start with what do we mean by a recurrence relation. Now let's suppose we got the sequence, all right? And this sequence we have the 0 term, term 1, term 2, until term n. Now the recurrence relation is the equation that relates those terms to each other. All right? So a recurrence relation is the equations that tell me the relation between those terms. All right? And we have something else is the initial condition, where we usually represent it as a 0. So the initial condition for the recurrence relation is a set of a value that explicitly defines some of other members. All right? Recurrence relation is the equation that relates each term in a sequence to other, and we have something called initial condition. It might be 1, which is usually considered as a 0, or it might be more than one initial condition. And we will see this more deeply in the upcoming examples. Let's start with this example. Now here it asks us to find the first 5 terms of a sequence satisfying the given recurrence relation as an is equal to 2an minus 1 plus n squared. If n is greater than or equal to 1, and I've got initial condition equal to 1. So if we go back to the definition, we saw that I've got a sequence that has a 0, a 1, 2, 3, a 4, a 5, and we can keep continuing until we reach a n. All right? Now the numbers are here indicate the position of the term. Where is exactly this term? So this is in position 0, this is in position 1, and this is in position 2. And this position is usually used in the recurrence relation as n. All right? So if we take, let's say that from here we can see that initial condition, which is a0, is equal to 1. So I got in this sequence the first term, which is 1. Now in order to find the second term, I need to solve this recurrence relation. So here we got that if I need to find a1, then a1 is equal to 2a1 minus 1 plus 1 squared. Now this is equal to 2a0 plus 1. 1 squared is 1. Now from the question I can see that a0 is equal to 1. So this is equal to 2 times 1 plus 1, which we got 2 times 1 is 2 plus 1 is 3. Okay, so here we got that the second term in this sequence is equal to 3. Now let's move to the third term, which is A2. A2 is equal to A 2A2 minus 1 plus 2 square. All right, this is equal to 2A1 plus 4. And here we got that 2 times A1 is equal to 3, or what we got here. So 2 times 3 plus 4 is equal to 2 times 3 is 6, and plus 4 is equal to 10. So here we got that A2 is equal to 10. Let's move to the fourth term, which is A3. A3 is equal to 2 times 3 minus 1 plus 3 square. And this is equal to 2A. 3 minus 1 is equal to 2 plus 3 square is 9. So this is equal to 2 times, we got that A2 is equal to 10. So here 2 times 10 plus 9. 2 times 10 is 20 plus 9 is 29. So here we got that the fourth term is equal to 29. We'll continue to the fourth term. So this equal to A 2A 4 minus 1 plus 4 square. And here we got that this is equal to 2A. 4 minus 1 is 3, so 2A3 plus 4 square is 16, and this is equal to 2 times 29 plus 16, and here we got is equal to 74. One last term, which is A5, and A5 is equal to 2A5 minus 1 plus 5 square. And here we got that this is equal to 2A4 plus 25. And here we got that A4 is equal to 74 plus 25, and this is equal to 173. Now from here we got the first 5 term beside the initial condition. So 1, 3, 10, 29, 74, and 173. So here from the recurrence relation and the initial condition we got the sequence. Now let's check the second example here. Again, we need to find the first 5 terms of a sequence which satisfying the recurrence relation and initial conditions. And if you notice here, I've got more than one initial condition, which is A0, A1, A2. That's why in the question, it asks us that we can start from n equal 3, which is the 4th term in the sequence. All right, so let's find the first 5 terms of the sequence. I've already got 0, 1, 2, and we will find like 3, 4, 5, and 6. All right, so here we got that A3 is equal to A3 minus 1 plus A3 minus 3. 3 is the position of the term that I'm looking for. All right, so this is equal to 3 minus 1 is 2, and 3 minus 3 is 0. So now we need to substitute the values of A2 and A0. A2 is equal to 0 plus A0 is equal to 1. So here we got that A3 is equal to 1. Now A4 is equal to A4 minus 1 plus A4 minus 3. And this is equal to A3 plus A1. Alright, now the value of A3, we already got it here as 1 plus A1 is equal to 2. So 1 plus 2 is 3. Alright, A5 is equal to A5 minus 1 plus A5 minus 3. 5 minus 1 is A4 plus 5 minus 3 is A2. The value of A4 is equal to 3 and the value of A2 is equal to 0, and 3 plus 0 is 3. A6 is equal to A6 minus 1 plus A6 minus 3. And here we got 6 minus 1 is 5 plus 6 minus 3 is 3. Now the value of A5 is equal to 3 and the value of A3 is equal to 1. 3 plus 1 is 4. Final term is A7, and here we got that A7 minus 1 plus A7 minus 3. 7 minus 1 is 6 and 7 minus 3 is 4. The value of A6 is 4 plus the value of A4 is 3, and 4 plus 3 is equal to 7. Yeah? Okay. Now I got the sequence as the initial conditions here is 1, 2, 0. Then we find already A3, 4, 5, 6, and 7, which they are 1, 3, 3, 7. Okay, so from here we note that the recurrence relation is defined in terms of previous term. I can find the value of the third term if I've already got the value of the second and the first, and the same for the rest. All right? Okay. Now let's see the vice versa. Let's see if I've got this sequence, am I able to find the recurrence relation or not? Okay, and here we will identify a new thing, says that explicit formula for the pattern of the sequence. All right, now the explicit formula has another name, which is the nth name, where it is the equation that help me to find a specific term. What do you mean by this? I can find the term n without knowing the relation between the terms. For example, here, if I couldn't find the value of A4, then I'm not able to find the value of A5, because this term is effect on the next term. All right, and this is what we know as the recurrence relation. However, the explicit formula, or we know as the nth term, is the equation of a specific term. So I can find any value in the sequence without knowing what is the relation between the term. and we call this as explicit formula or the nth term. And then we can find the recurrence relation in the initial condition, where we can see the relation between the terms in the sequence. So let's start here with the explicit formula. We got the sequence as 3, 5, 7, and 9, and we are trying here to find the relation between the term and its position. Okay, so here my sequence is A0, A1, A2, A3, and so on. And here we got that this is equal to 3, 5, 7, and so on. Now I need to find the relation between the position and the value, not between the term. All right, so if we notice here, 3 is equal to 2 times position 1 plus 1. Okay, let's see here, 5 and 2 is equal to 2 times 2 plus 1, and here we got 5. If we check here, 7 and 3, what is the relation between them? If I multiply 2 by the position, which is 3, and then add to it 1, it will give me the value of this term. So from here, we got that the nth term, or the explicit formula, is equal to n times 2 plus 1 for all n is greater than or equal to 1. Or we can have it as 2n plus 1. Okay, so the explicit formula, or the nth term, as usually represents the relation between the position of the term and the value of it. Okay, now let's move to the recurrence relation and the initial condition. I've got the sequence as 3, 5, 7, 9. And all what I need to do is find what is the relation between this term and this term, and between this, and so on. Okay, so if we can see here, 5 is equal to 3 plus 2. 3 is the previous term. Okay, now let's see if this again happened with the next term. If we see 7 is equal to 5 plus 2. So here we got 5 as this term. So 7 is equal to 5 plus 2. All right, let's check here. 9 is equal to 7 plus 2. So from here we can see that an is equal to the previous term, which is n minus 1 plus 2, right? And here we got that the initial condition A0 is equal to 3. So we can start from 1. And here we got the recurrence relation. Okay, this is the recurrence relation, and we can have it as RR. And this one is the initial condition. Now the combination of the recurrence relation and the initial condition give me the recursive definition. Okay, so here we got the explicit formula where the relation between the value of the term and its position. And here we got the recursive definition definition, sorry, where I am trying to find the relation between the term and the previous terms. And it's really important we mention the initial condition and from where I can start to find the terms. Let's see this example now. Consider the sequence 1, 1, 2, 3, 5, 8, 13, 21, etc. We need to find the recurrence relation and its initial condition for the sequence. So we says that recurrence relation and initial condition give me the recursive application. Sorry, the recursive definition. Okay? So we need to find the recursive definition of the following sequence. And when I say the recurrence relation, I need to find the relation between the terms in the sequence. Okay? With the none of initial condition. So if we start from here, let's say A0 is 1. A1 is also 1, which is nothing with A0. Okay, now let's see A2. A2 is equal to 2. And 2 is 1 plus 1. Alright? A3 is equal to 3. And 3 is 2 plus 1. A4 is equal to 5. And here we can see that it is equal to 3 plus 2. Now from here we can see that A2 is equal to A0 plus A1. And here we got that it's equal to A1 plus A2. A4 is equal to A2 plus A3. So from here we can see that AN is equal to AN minus 2 plus AN minus 1. Okay, so 2 is equal to the first term plus the second. 3 is equal to the second plus the third. Fourth is equal to the third and the fourth. Okay, so AN is equal to AN minus 2 plus AN minus 1. And the initial condition, or we have it here as two initial conditions, which are A0 and A1. Okay, so A0 equal to 1, A1 equal also to 1. And from here we can see that N is greater than or equal to 2. So we got here the recursive definition where we have a recurrence relation and the initial condition. Now, if we notice from this example, we can see that the recurrence relation have two initial conditions. So some of the sequence, we might have even more than two initial conditions, 3 or more. All right. Therefore, we have to decide how many initial conditions for the sequence, and obviously it's required on the recurrence relation itself. Okay, now let's move to the second part of our session here, and we're still in lecture 7. So we can have the recurrence relation, and from the recurrence relation we can create this sequence. We usually write the recurrence relation as function. So for example here, the function of n is equal to 2fn minus 1 plus fn minus 2 for all n is greater than or equal to 2, And here we got that f0 is equal to 5 and f1 is equal to 7. It is something like an is equal to 2an minus 1 plus an minus 2. However, we can see that here it is in different shape. Alright, so let's try to solve this and find the sequence. Here we got that f, we start from 2. So f of 2 is equal to 2 f of 2 minus 1 plus f of 2 minus 2. So here we got that this is equal to 2 f 2 minus 1 is 1 plus 2 minus 2 is 0. So from the head of my question here, we can see that f1 is equal to 7. So here we got that 2 times 7 plus f0 is 5. So this is equal to 19. Okay, now let's see. f3 is equal to 2f3 minus 1 plus f3 minus 2. And this is equal to 2f 3 minus 1 is 2 plus 3 minus 2 is 1. So here we got f2 is equal to 19. So 2 times 19 plus f1 is equal to 7. And here we got 2 times 19 plus 7 is equal to 45. f3 for n is equal to 4. Sorry, f4. f4 is equal to 2 f of 4 minus 1 plus f of 4 minus 2. And this is equal to 2 f of 3 plus f of 2. So here we got that 2 times f of 3 is equal to 45 plus f of 2 is equal to 19. And here we got that it is equal to 109. So from the recurrence relation mentioned here, I can have the sequence as 5, 7, then 19, 45, 109, and it can be continued. Okay? All right. Another example here where we can consider the function, okay, defined by f of 0 is equal to 1, f of n is equal to n times f of n minus 1 for all n is greater than 1. Okay, again, if we start from 1, so f of 1 is equal to 1 times f of 1 minus 1. So this is equal to 1 times f of 0. And here we got 1 times 1 equal to 1. Then we move to the second term, which is f of 2. f of 2 is equal to 2 times f2 minus 1. So here we got that it is equal to 2 times f of 1. And here we got that 2 times f of 1 is equal to 1. So 2 times 1 is equal to 2. If we see the third, f of 3, we got here 3 times f of 3 minus 1, which is equal to 3 times f of 2. And here we got that 3 times f of 2 is equal to 2. So 3 times 2 is 6. Alright, now f of 4. equal to 4 times f of 4 minus 1, which equal to 4 times f of 3. So here is equal to 4 times f of 3 is equal to 6. So 4 times 6 is equal to 24. Now if we notice here, this is equal to 1 factorial, this is equal to 2 factorial, here we got 3 factorial, and here we got 4 factorial. If we continue, we can see that this sequence is for the factorial sequence, where we got it as 1, 1, 2, 6, 24, 1, 2, 0, 7, 2, 0, and so on. So sometimes we can have multifunctions for the same sequence. So for factorial, it can be as n times f of n minus 1, or it can be f of n is equal to n factorial. For all n is greater than or equal to 1 or 0. And here we reach the end of lecture 7, where we discussed about if we got a recurrence relation and initial condition, how we can find the sequence, and for if we got the sequence, how I can find the recurrence relation and initial condition.